So Dr. C, problem number 1 from homework 13 is about a bridge that the university constructs to help students get across Euclid Avenue without waiting for lights. But the key element of this bridge, which we can think of as a beam, okay, which has a mass m and a length L, m sub b for mass of bridge, to distinguish it from the mass of the students who will be on the bridge. So it's a uniform beam of mass m sub b and length L that's supported on its left end by a hinge and on the right end by a wire rope that heads up to a tower at an angle theta. Okay, so you're asked to calculate the tension in this rope, and later on you're going to be asked for the forces that the hinge have to be supplied so that the students can safely make it across the bridge. The students have a mass m sub s, and at any given time they're a distance x from the left side of the hinge, or left side of the bridge where the hinge is. Okay, so hopefully you can see that this is a statics problem, and what we know for a statics problem is that the sums of the forces on the bridge have to be 0. It's a vector relationship, and similarly the sums of the torques acting on the bridge have to be 0, because we don't want any translational acceleration or angular acceleration of the bridge, because that will make it fall. Okay, so let's start by constructing a free body diagram that shows the forces and the torques. So I'll just redraw my beam down here. And what we've got is the gravity, which will act at the center of mass of the bridge, will pull down with a force m sub bg. The students, wherever they are, will lead to a force mass of the students g acting downward. Now it's actually a normal force between the students and the bridge, and so m sub s g doesn't act directly on the bridge, it acts on the students, but because the students aren't accelerating with respect to the bridge, that normal force has to be equal to ms. So I'll just simplify things and draw it that way. Notice that this distance is L over 2, and this distance will be x, because we'll assume we're using an x-axis that's horizontal, and I'll put the origin to coincide with the hinge, and my y-axis will be up, the conventional up direction. And note that this means that the z-axis will be x cross y z, so z is out of the page towards you, and we'll need that when we calculate the torque due to all the forces. And we also have the tension pointing up at an angle theta. So those are all the forces, well, not quite all the forces, the tension, the two forces of gravity, but there's also a force from the hinge, and so that could have both x and y components, and I don't know the directions, so let's just assume they're positive for now. So those are the hinge forces, which have both x and y components. That we'll have to figure out for part C, but we don't know yet. Okay, so how do we proceed? Do you start with the sums of the forces on the bridge or the sum of the torques? And if I think about the sums of the forces, remember it's two equations, f sub x and f sub y, and what I know and don't know, well, I know these two masses, but I don't know the tension, I don't know the hinge forces. So if I write out any one of these things, I'll have an x component of the tension, an x component of the hinge force, two unknowns, one equation. I won't get very far. The same thing goes if I try to write the sums of the forces in the y direction. I won't get very far. But that's two equations, and we also have a torque equation. And so I can write down the sums of the torques at any given point, and that gives me 3 total equations. So I could write them down in principle in any order, have 3 equations for 3 unknowns, and ought to be able to solve them. But there's a best way to approach this, because if I start with these 2 equations, the x and y components, I won't get anywhere quickly. But if I start with the sums of the torques about the bridge, acting on the bridge, then you'll see that things work out a little bit more simply. You don't have to do it this way, but it will, I think, work out for the best. So what I want to do is write down the sums of the torques on the bridge, but now I'm faced with where do I calculate them, about what axis. I think it seems natural to calculate about the hinge, but you should think about this. The advantage of calculating the torque with reference to the hinge is that the torque due to these two hinge forces goes away. It's zero because torque equals R cross F, and R points from the axis of rotation to the point where the force acts, and that's zero. R is zero if you use this as your reference point because the forces both act there, so there's no distance from that point to where the forces act. So you actually get rid of these two forces in the sums of the torques equation. You'll be left with only T as an unknown, and that will be easy to solve as a standalone equation. So that's the logic here. So I'll do the sums of the torques acting on the bridge about the hinge, and now I just start writing out the terms. Okay, well, there's the torque due to the students. Now remember we went R cross F. That'll be, and you can think of this as a few different equations, the component of R perpendicular to F, or the moment arm, or times F, or R times the perpendicular component of the force, or RF sine theta, where theta is the angle if you put them the vectors tail to tail. So let's see what's easiest here. R from this point to the point where the weight of gravity, the force of gravity acting on the student's acts, is just x for R. That's this distance. The force is msg. Okay, so that's one of our terms. And the direction for that, R points this way, F points down, so my thumb is into the page. So if I'm going to write things in terms of z, I'm going to need a negative sign there, and I'll have a z hat somewhere here on the right. Okay, how about the force of gravity acting on the bridge? Well, that force acts a distance L over 2 away, and of course R and these forces are perpendicular, so sine will just be 90 degrees, but also we want the component of R perpendicular to F, and that is just this distance. So I have another negative term, L over 2 mbg. This is the mass of the bridge now. And now I have to get the torque due to the tension in the string. Well, first of all, this will be positive because R cross F will be out of the paper towards you. So this will be a plus. And now I have to decide which of these three expressions to use. And R perpendicular would say, well, imagine a line going up here perpendicular to the tension. Well, that's a bit of a pain. But what's a little bit easier is to imagine the component of the tension perpendicular to this R vector from there to there. Okay, well, this distance, by the way, is L, so R is equal to L. And the component of T perpendicular to this R vector is just T sine theta. So I just write T sine theta. So this will be the sums of the torques, will be these three terms in the z hat direction, and those have to be equal to 0. Okay, if you now just think for a moment what I've got here, all of these factors are known. Well, at least you're asked to write the tension in terms of x, and so you can imagine that x is something that belongs in your answer, and that these quantities are all known or given to you. The numbers are given to you in part B. So all I want to write is an expression for t in terms of everything else. It just means rearranging this. Take these two terms to the right side of the equation, divide everything by L sine theta. I've got the tension equals the mass of the students times x plus the mass of the bridge times L over 2 divided by L sine theta. And both of these terms multiplied by g, I just like to have that separately, a matter of taste, I guess. So that's the answer to part A. Okay. Calculate t in terms of the distance x of the students and the parameters given in the problem statement. Part B is straightforward, I hope. It just gives you some values for all the masses, and you just have to plug those in. So you're given the masses of the students as sums to 1,000 kilograms. They're going to be standing 20 millimeters at the far end of the bridge, because we'll make x equal to L to see if you can have things hold up whenever they get all the way across the bridge. The mass of the bridge itself is 2,000 kilograms. And L over 2, half the length of the bridge, is 10 meters. L appears again here for the torque due to the tension in the string, so that's 20 meters. And you're told that theta is sine of 45 degrees. So take all this, well, then you have to multiply by 9.81 meters per second squared. Plug all this into your calculator, and you'll find the tension is 2.78 times 10 to the 4th newtons. Okay. And you could think for a moment, if you want, does this seem reasonable? But the scale is certainly sensible. You can imagine if you were just hanging things vertically from a rope like this, you would have a total mass of 3,000. Well, you would have a 20,000 from here and another 10,000 from there. And that would be the force you would need. And that's comparable to what you need for this. So at least we're in the right ballpark. Okay, part C then says, what now is the force of the hinge? Okay, which I didn't want to attack at first because we didn't know the tension in the rope, and that was going to make it hard to calculate the force in the hinge. But now it's straightforward, because now I can use the sums of the force in the x direction. Remember, this is a vector expression, so I should, when I use it, have to break it down into x and y components. So that's the force of the hinge is x component minus t cosine theta. Okay, that's just assuming that the force of the hinge is positive, so it's a positive x. The x component of the tension is t. Remember, this is theta here. This t cosine theta. Those have to sum to 0. So I could solve this quickly for h. The force of the hinge in the x direction is just t cosine theta. Okay, so just plug in the value for t that we've got here, and theta equals 45 degrees. And you find 1.97 times 10 to the 4th newtons. And the sum of the forces in the y direction, similarly, I assume the hinge force is positive. If I'm wrong, I'll just get a negative sign. That won't happen in this case, though. But in the y direction, remember, I have the force of the hinge, but I also have these two weights and a y component, which is t sine theta. So I have to include all those. So the gravity is applying a force in the negative direction of the sums of the masses times g. The tension is acting in the positive direction, and the vertical component of the tension is t sine theta. Okay, and of course, these are equal to 0, must sum to 0. So I can solve this for the force of the hinge in the y direction is equal to the sums of the masses times g minus t sine theta. Okay, it's minus t sine theta because the y component of the tension helps to hold things in the vertical direction, so the hinge doesn't have to do it all by itself. Just plug in all the values that you're given above. 3,000 kilograms, 9.81 meters per second squared, minus 2.78 times 10 to the 4th newtons, times the sine of 45 degrees. Plug that into your calculator, and the answer is 9.77 times 10 to the 3rd newtons. Now, this would seem like a complete answer, the x and y components of the hinge force, but you're actually explicitly told get the magnitude of the force. Not bothering with the direction, but the magnitude of the hinge force then is just the square root of the sums of the squares of these two components, or 1.97 times 10 to the 4th newtons squared, plus 9.77 times 10 to the 3rd newtons squared, square root of that, and so the answer is 2.2 times 10 to the 4th newtons. And that's what you're asked for. If you were also asked for the direction of the hinge force, you would just say the arc whose tangent is the y component over the x component, but you weren't asked for that. So that finishes Dr. C number 1.